So in this video, we're going to cover the very basics of quantum computing. We're going to approach all the foundational concepts from a qualitative standpoint and give you the sort of basic understanding you'll need to approach anything else in the field. So to start off with, we're going to discuss the concept of qubits and how they differ from how we classically store information. And then we'll move on to the idea of superposition and measurement, which are what make quantum computing so fundamentally different from classical computing. And finally, we'll touch on the concept of entanglement between multiple qubits. So to understand qubits, it helps to compare them first with classical bits, which are how we normally store information. Now, as you likely already know, a classical bit can store either a 1 or a 0. These are the fundamental pieces of information that make up even the largest pieces of data. Now, there are a few ways that we store this classical information, and one of them is called magnetic storage. Now, in magnetic storage, we take a sample of magnetic material and we divide it up into little patches. Each of these patches can then be magnetized with the magnetic moment pointing up or down in different places. And we can then assign each of the sections that are magnetized up to be representing the bit 1, and sections that are magnetized down to be representing the bit 0. So using that, I have just stored the string 1010. Another option is transistor-based storage. Now, this is used in stuff like flash memory, and it essentially consists of what you can think of as an array of tiny little boxes that can either be empty, representing the bit 0, or be filled with electrons, representing the bit 1. Now, for any classical bit, you have precisely these two options, nothing more, nothing less. Each individual section of magnetic storage would either store a 1 or a 0, or each individual transistor in transistor-based storage would either store a 1 or a 0. Now, when it comes to qubits, there are many different options out there. One option you may be familiar with is that of a spin-based qubit. Now, in spin-based qubits, you take something like an individual electron, and you can encode data in the direction of its spin. Now, each electron has an intrinsic spin, which is sort of like the direction of its magnetic north pole. And you can encode data so that whenever the spins are pointing directly up, or in the plus z direction, we call that a 1. And anytime the spins are pointing down, or in the negative z direction, we call that a 0. Another option is something called a superconducting qubit. Now, in these qubits, you use something called a superconductor, and you can create a little loop of superconducting material. And because of some interesting physics that happens at these scales and at these temperatures, you can either have a current that flows in one direction, or you could have a current that flows in the opposite direction. And what you can do is you can effectively use these as your two fundamental bits and store, for instance, a counterclockwise current as a 1, and then a clockwise current as a 0. Another example is used in photonics. So in photonic quantum computing, you can use something like the polarization of a photon to encode your data. So photons are little packets of electromagnetic waves, and for instance, they could oscillate so that the electric field changes from pointing up to pointing down, or they could instead be polarized in the opposite direction, where they are either coming into or out of the screen here. So you can use a vertical polarization as a 0 and a horizontal polarization as a 1, for instance. What makes quantum computing so interesting is the concept of superposition. Because unlike in classical computing, with superposition, our quantum information can be in a combination of the 0 and the 1 state at the same time. Now, to understand what I mean by that, we'll use the example of spin qubits specifically. So, for instance, I can have a spin up or a spin down particle. But as I'm sure you could guess, we can also have a spin that is effectively pointing in some other arbitrary direction, right? For instance, pointing to the right. Now, what's interesting in quantum mechanics is that when we take a measurement of a quantum system, you pick something called a basis. So all a basis is it's a selection for what we mean as R0 and what we mean as R1. Now, despite this electron being in a state where its spin is essentially pointing to the right, when I measure it in this basis, which is essentially asking whether the spin is pointing up or pointing down, I will always receive one of the two answers. I will either get that it is pointing down or that it's pointing in the up direction. I will never get anything else. So when I have a spin that is pointing perfectly to the right, we say that it is in an equal superposition of being in the 0 state and in the up state. Now, this concept is sort of strange and very unique to quantum mechanics, but it is the absolute foundation of everything that we do in quantum computing. So, for instance, I can say that this one has a 50% chance of being measured as a 0 and a 50% chance of being measured as a 1. Now, you get the same idea of superposition in all the other forms of qubits. Probably the other easiest one to explain is photonics, where I can take a vertically polarized photon and a horizontally polarized photon and add them together so that I get a photon that is essentially polarized in the 45-degree direction. So it probably helps if I instead draw it this way. So I could either have one that's polarized vertically or polarized horizontally, but I can essentially add them together to get a photon that's polarized in this 45-degree direction. Now again, in photonics, our basis in this case is going to be either the vertical or the horizontal polarization. So when I measure this 45-degree polarized photon, I will always get either a vertical or a horizontal polarization. Since this 45-degree polarization is exactly in between these two basis states, I will again get a 50% chance of being vertically polarized and a 50% chance of being horizontally polarized. Of course, I don't always need to have a perfectly equal superposition, and instead, if I'm going back to my spin-based qubit, I could have a spin that is pointing mostly upwards, but not perfectly up. So in this case, I can say that if I'm measuring it in the up and down basis, I could have, for instance, an 80% chance that it's pointing the up direction, since it's very closely aligned with that. But I could still have a 20% chance of measuring it to be spin down. And in fact, I can choose my superposition so that I have an arbitrary probability distribution between my two basis states, right? So I could be swapped the other way, for instance, if I had a spin that was pointing mostly downwards, or if I start my spin out pointing perfectly up, I will get a 100% chance that it is measured pointing up and a 0% chance that it's measured to be pointing down. Finally, we can discuss the concept of entanglement between photons. Now, you may have heard entanglement called spooky action at a distance, and while it is quite strange, it's by no means magical. The best analogy that I've heard for entanglement is to imagine having two pairs of socks. I could have a white pair and I could have a black pair of socks. Now, let's say that me and a friend of mine are packing our suitcases to go for a trip. But while we're packing, we accidentally jumble up the two pairs of socks. All I know is that each suitcase has exactly two socks, but I don't know whether they're white socks or whether they're black socks. Now, if I take my suitcase and I open it, and I find that I have one white sock and one black sock, I automatically know that my friend's suitcase must have the other white sock and the other black sock. Similarly, if I open my suitcase and I see that I have two black socks, even if my friend is on the other side of the planet, I immediately know that my friend has the pair of white socks. So, in essence, the information about which pair of socks I have is entangled with my friend's pair of socks. So, what this means is that whenever I open my box or my suitcase, I immediately gain knowledge about what my friend has, and vice versa. So, this also means that there are certain combinations of pairs of socks that would never appear. For instance, no matter what happens, no matter who opens whose suitcase first, we'll never see a combination where I have two black socks and my friend also has two black socks. Or if I end up with a pair of white socks, I immediately know that my friend must have zero white socks. However, an important caveat to this analogy is that because of the nature of quantum mechanics, the socks themselves would not have a well-defined color until we actually open the suitcase. Now, this is somewhat related to the idea of Schrödinger's cat, which you may have heard of. And more specifically, it relates to the idea of a lack of hidden variables in quantum mechanics. But these are slightly more advanced topics, so we'll save them for another video. So when it comes to what entanglement looks like in a qubit, for instance, I could return to the idea of photonics. So when I generate a pair of entangled photons from a crystal, for instance, it can be generated in a way where we know that one photon has to be vertically polarized and the other has to be horizontally polarized. Now, I don't know which photon is which, but if I set up a detector here and a detector here, the information about their polarizations is entangled. So if I get that the first detector gets a vertical polarization, I automatically know that my second detector should have received a horizontal polarization, and vice versa. I similarly know that if I measure a horizontal polarization on the first detector, then it is impossible for me to get a horizontal polarization on the second detector. So in that way, the information stored in my two qubits has been entangled together. So to review, if I have a superposition of states, all this means is that when I take a measurement, I have a probability to get a zero, right? I have some percent chance to get a zero and some percent chance to get a one. So to physically realize this, I could have, for instance, a spin pointing in some arbitrary direction, or a polarization of light that's in some other random angle. And then if I want to entangle my information together, I can create a system where information about one qubit automatically reveals something about the other. So the example that we used was where a vertical photon and a horizontal photon are simultaneously created. And this is directly analogous to the idea of having a white pair of socks and a black pair of socks. So whenever I measure my photon at a detector, whatever my measurement is on one photon automatically sort of collapses the information about the second photon. I hope this video has given you a better understanding of the general concepts in quantum computing. Be sure to watch our other videos to get a deeper understanding of how to do calculations and how to use these concepts quantitatively, as well as how we could implement this to do useful quantum computing. Thank you.